Welcome to the forefront of transportation innovation, where the future meets the present, the world of Hyperloop. In this captivating journey, we'll delve into the intricacies of the Hyperloop pod, a marvel of engineering and technology reshaping how we envision high-speed travel. The Hyperloop, a brainchild of Elon Musk, is not just a mode of transportation, it's a revolution. Picture a network of low-pressure tubes where pods, levitating on magnetic fields, race at mind-bending speeds, drastically reducing travel times. It's an idea that challenges the norms, pushing the boundaries of what's possible. Our guide on this fascinating journey is a lecture, a deep dive into the mechanical, electrical, and propulsion subsystems that breathe life into the Hyperloop pod. This lecture is crafted by loopMIT, a student project housed in the prestigious MIT Manipal. As we navigate through the intricacies of this lecture, we'll unravel the secrets behind the mechanical subsystem, where precision engineering meets structural integrity. The electrical subsystem, a symphony of currents and circuits, will unfold, revealing the intricate dance of electrons that powers this revolutionary pod. However, our focus today transcends the ordinary. We set our sights on the beating heart of the Hyperloop pod, the propulsion subsystem. It's not just about movement, it's about propelling us into a future where speed and efficiency converge.
Hello everyone, we are loopMIT and we welcome you to today's lecture. To give you a brief about loopMIT and our team, it was founded by Prayan Gupta and Jash Shah in the close of 2018 and emerged as one of the university's most youthful student project teams. The genesis of loopMIT took shape when friends Jash and Prayan stumbled upon MIT's Hyperloop paper. Enthralled by its potential, scalability, and green technology, they envisioned an organization dedicated to advancing this technology here in Manipal itself. Their enthusiasm led to a proposal for the demo of a presentation to the college, showcasing simulations and detailing Hyperloop's advantages. Fortuitously, the college endorsed their vision and officially named loopMIT as one of its student projects. Subsequently, they initiated recruitment by tapping into other student projects and students across the university. The team's nascent phase encountered successive obstacles. The research phase, delving into levitation and propulsion infrastructure, involved hydraulics testing and constituted a challenging trial period. Given the novelty of Hyperloop technology, the hands-on initiation proved to be intricate. This resulted in several members dropping out due to its demanding nature. The absence of individuals with a visionary perspective and an understanding of the project's intricacies posed a significant challenge. Despite these setbacks, the team weathered the storm and regrouped in 2021 with a renewed commitment to improvement. Setting their sights on the European Hyperloop Week 2022, the team progressed into the manufacturing phase. Overcoming challenges such as trial and error, budget constraints, and recruitment difficulties, the team successfully cleared the first stage of EHW 2022 and 2023. The subsequent year witnessed further team expansion with passionate members joining the ranks. Collaboratively, they embarked upon building our first Hyperloop prototype, cognizant of the challenges faced by their predecessors. Currently, our team is manufacturing a complete pod for the EHW 2024 competition.
As we transition to the mechanical subsystem, envision the beating heart of the Hyperloop pod. The loopMIT lecture, a captivating insight into this realm, delves into the engineering symphony that forms the backbone of high-speed travel. From structural fortitude to aerodynamic prowess, each component is a testament to the meticulous craftsmanship propelling the Hyperloop pod into the future. Join us in unraveling the core of innovation within the mechanical subsystem.
Hello. Let us start with the mechanical subsystem. This subsystem consists of components such as air shell, chassis, braking system, lateral control modules, and vertical stability system. On my right, you can see the isometric and side views of our pod, while on the left, you can see the mass specification table of each component. Moving on to our first component, air shell. The air shell is a critical component for the pod, since it protects the pod's components while also assisting the propulsion system in moving the pod more efficiently by causing less drag. The air shell has been built in such a manner that it will feel as if it is traveling in vacuum. We had several prototypes of the air shell but we've picked this one to make the pod appear more streamlined. Moving to our second component, chassis. As you can see, our chassis is an inverted U structure. Initially, we designed a monocoque structure, but it was not structurally compact enough during high speeds, and it was hard to mount all the different components without affecting the stress limit in the chassis. That is why we have selected this structure. This provides mounting points for the brakes, LIM, suspension, battery pack, pneumatic cylinders, and the air shell. Moving to our next component, that is braking system. As we know, a hyperloop runs on very high speeds. Hence, it is necessary to apply proper braking at proper intervals of time to avoid accidents. In our current prototype, we are using frictional brakes with pneumatic actuators to carry out the braking. The brakes have a clamp-like structure. They apply pressure to the upper flange of the I-beam.
With the mechanical intricacies unraveling, we seamlessly transition to the pulse of our Hyperloop pod, the electrical subsystem.
Greetings. I'll be explaining the things that we have taken under in our subsystem. So the very first thing that we have is the battery management system. So the battery management system basically is designing of the battery pack and giving the value of voltage and current through which we will be able to power the entire pod. The battery management system not only includes the battery pack, but also it includes the discharge rate and the C rate, as we call it, or various other rates of charging as well. So we are able to determine and we are able to configure the entirety of the battery management system and how it is going to be implemented in the pod. So it is all manual, so that we are able to control what goes where and how much current and power and voltages are required. Here are some of the briefs that we have taken under. Moving along, the second thing we have are sensors. Sensors are basically that measure the change in the physical environment of a particular sensor. So in sensors, what we are going to do is monitor the internal and external conditions of the pod. It may be stationary or in motion. Various kind of sensors will be implemented in various parts of the pod as per the requirement. There may be thermal sensors detecting the heat of the battery pack systems, or there may be a distance sensor that will measure the distance of the pod from the ground. That will be very minimal, but still it will give us a value. And if there is any situation in which when brakes are to be implemented, it will show us that value. So those are sensors. It basically senses the change in the physical environment. GUI, graphical user interface. That is another part of our electronic subsystem. It is basically the external control that we are going to give to the user so that he could control the ins and outs of the pod. He will be able to monitor all the data that is incoming from the sensors as previously mentioned, and he will be able to run the pod accordingly and as per the requirement. The next thing we have is the PCB design. The word PCB means printed circuit board. We print it as per our requirement. How much sensors do we need? Where all do we need? What are the microcontrollers we are using? So these are some of the things that we have currently taken under and we are currently working on in the electronics domain of loopMIT. Thank you.
Embark with us on a journey through the tapestry of modern transportation. Whether defying gravity in the skies or gracefully gliding on the ground, every mode and vehicle is intricately woven into the fabric of one fundamental concept: propulsion. Let's delve into the very heartbeat of groundbreaking innovation. Join us as we unveil the technology that propels the future of travel, the intricate traction subsystem of the Hyperloop pod. Picture a transportation future that breaks barriers. The Hyperloop pod. It's not just a ride, it's a gateway to what's next. As we journey through time, linear motor-driven railway systems reveal their presence in mass transit like the Yokohama Municipal Subway, a testament to short-stator linear induction motors. Maglev systems, on the other hand, unfold across forward development from electrodynamic levitation systems to controlled permanent magnetic levitation systems. Rewind to the 1960s, where Great Britain led maglev research. Visionaries like Eric R. Waite pioneered the linear induction motor. In 1969, US inventors James Powell and Gordon Dandy patented the superconductivity maglev concept. Fast forward to the 1970s, an era of collaboration and competition among the United States, Germany, and Japan, each exploring the electrodynamic principle with superconducting magnets. The quest for speed reached remarkable milestones. In 1979, Japan set a world record of 517 km per hour with the superconducting electrodynamic system. Britain too embraced the iron core long stator motor, paving the way for the world's first commercial automated maglev system in the 1980s at Birmingham International Airport. Fast forward to the 1990s, and the baton of innovation passed between Japan, Germany, the United States, South Korea, and China. The Chubu test line in Nagoya witnessed the high-speed dance of the HSST system. Meanwhile, Germany's Transrapid test track evolved, and the United States embraced the MagneMotion urban maglev system, demonstrating the versatility of permanent magnets in conjunction with control coils. But the story doesn't end here. As we cast our gaze towards the future, one technology stands poised to redefine transportation: the Hyperloop, a visionary leap into the next era. The Hyperloop promises to seamlessly connect distant cities at unprecedented speeds, propelled by the very principles we've explored today. At the epicenter of Hyperloop's incredible speed lies the secret ingredient: traction. Imagine it as a magnetic dance choreographed by the single-sided linear induction motor. This cutting-edge technology transforms magnetic fields into a graceful propulsion force. Let's start at the heart of the matter: linear induction motors. Imagine unrolling a conventional rotary motor, creating a flat, single-sided marvel. In our case, we're utilizing a single-sided linear induction motor featuring a short stator, core and coils, and a long rotor aluminum track. It's the force behind the pod's propulsion, and today, we're dissecting its intricacies. Let's meet the key players: the short stator snugly placed on the pod and its counterpart, the long rotor, gracefully lining the track. Together, they perform a magnetic ballet that propels the Hyperloop into motion. The short stator, embedded on the pod, provides compact power, while the long rotor along the track ensures a continuous, dynamic magnetic field. A duet of engineering marvels. The beauty lies in simplicity. Picture a rectangular slotted structure forming the primary or stator, with polyphase windings generating a linearly traveling magnetic field, much like its rotary counterpart. The secondary comprises a sheet conductor, creating the magnetic flux linkage. This interaction induces a voltage, leading to the generation of an eddy current, resulting in thrust in the longitudinal direction of the motor. But how does it fare in the real world? We've tested various configurations: a 6-slot 3-phase linear induction motor with a carbon steel core powered by an auto transformer. The results were promising, showcasing the movement of an aluminum plate atop the linear induction motor. Simulations including 24-slot and 9-slot linear induction motors have further fueled our understanding, mapping magnetic flux densities for optimal performance. One of the initial setups involved a 6-slot 3-phase linear induction motor with a carbon steel core. Our aim was to observe the motor's performance under specific conditions. For this test, we powered the SSLIM using an auto transformer, carefully adjusting the number of windings per slot. The winding configuration included 22-gauge and 19-gauge wires, strategically chosen to prevent overheating. The maximum current and voltage applied were 10 volts and 40 to 50 amps, respectively. The heart of our experiment lay in the observations of the SSLIM's reaction. Through meticulous testing, we placed an aluminum plate on top of the SSLIM to visually capture the induced motion. Fortunately, we have a video recording of this test, allowing us to witness the compelling results. As you can see in the video, the SSLIM demonstrated the linear motion we anticipated. This validates the concept of direct electromagnetic thrust propulsion, a key advantage of SSLIMs over traditional rotary induction motors. But our exploration didn't stop there. We ventured into simulations to understand how different slot configurations could impact the SSLIM's performance. we modeled 24-slot and 9-slot linear induction motors and simulated their magnetic flux densities. Our first simulation takes us to a 24-slot linear induction motor meticulously designed within the COMSOL multiphysics interface. The core material chosen for this model is electrical steel, a deliberate selection based on the superior performance observed in real-world testing when compared to carbon steel. In this simulated space, we analyze the magnetic flux, represented by intricate lines denoting the density of flux at various points within the 24-slot. This visualization offers a comprehensive understanding of electromagnetic interactions, a critical aspect in the optimization of linear induction systems. Transitioning to our second simulation, we maintain the focus on precision. The 9-slot linear induction motor simulation employs the same core material, electrical steel. Through this simulation, we explore the magnetic flux distribution in a contextually different structure. The magnetic flux visualization for the 9-slot LIM reveals a nuanced difference, showcasing a reduced density of flux lines compared to the 24-slot counterpart. This insight is pivotal in tailoring the design of LIMs for specific applications and performance requirements. Now, let's bridge the gap between these simulations and the tangible world, where the pulse of machinery and transportation dynamics come to life. Simulations, digital pioneers that they are, serve as crucial architects of practical innovation. Our journey through COMSOL multiphysics has not only demystified the complexities of LIMs, but has also paved the way for real-world applications. Having navigated the digital landscapes, let's dive into the foundational blueprints that govern the very essence of single-sided linear induction motors. Our next destination is the intricate realm of design, where equations and parameters converge to mold the heart of these technological marvels. Within the domain of single-sided linear induction motor design, a complex interplay of equations takes center stage. Terms like permeability of free space, stator current density, and slot pitch serve as the foundational elements shaping the stator's blueprint. These terms act as essential components, each playing a distinct role in the design orchestra. The permeability of free space establishes the groundwork, influencing magnetic field interactions within the motor. Stator current density governs the flow of electric current through the stator windings, infusing dynamic energy into the system. Simultaneously, slot pitch orchestrates the spatial arrangement, ensuring a harmonious coordination of magnetic forces. As these elements seamlessly intertwine, they give rise to the equivalent circuit model. This model acts as a practical guide, revealing the intricacies of the motor's behavior. Governed by these equations, engineers gain valuable insights into the motor's responses under different conditions, allowing for a comprehensive understanding of its nuances and accurate predictions of its performance. This convergence of equations isn't merely a theoretical construct. It serves as a practical roadmap for the implementation of SLIMs in the real world. Through this intricate web of mathematical expressions, we unravel the secrets of efficient propulsion, unlocking the potential of linear induction motors for tangible applications in various industries. In essence, this amalgamation of equations is both a nod to theoretical precision and a pragmatic tool steering us through the dynamic realms of motor engineering. Gaze upon Figure 3, a graphical embodiment of our equivalent circuit model, the very soul of the single-sided linear induction motor. Within its intricate lines and symbols lies the roadmap to unravel SLIM's latent capabilities. Armed with this circuit, we venture into the realm of force calculation, a pivotal metric governing the motor's prowess. This visual representation becomes our guiding compass, translating abstract equations into tangible forces that propel SLIM into act. It's not just a diagram. It's the gateway to decoding the motor's potential and harnessing its power for real-world applications. Figure 4 unfolds the dimensions of the secondary, a pivotal component comprising the reaction plate and conduction layer. Here, meticulous design choices come into play. A robust reaction plate, whether solid or laminated, coated with a strategic layer of aluminum or copper, sets the stage for optimal performance. For standard operating conditions, the reaction plate's thickness, not less than 6 mm, and the attached conducting sheet, not less than 3 mm, form the golden ratio. It's a delicate dance where the width of the secondary, the width of the primary, and the pole pitch harmonize in the equation shown. As these equations and design principles converge, we witness the birth of a mechanical symphony, where every term, every dimension plays a vital role in the performance of single-sided linear induction motors. In the intricate realm of linear induction motors, our voyage transcends theoretical boundaries, delving into a domain where challenges cease to be obstacles and instead metamorphose into gateways of innovation. This section serves as a profound testament to our odyssey, showcasing how each hurdle encountered along the way has evolved into a stepping stone, paving the path towards unprecedented and groundbreaking solutions. The genesis of our challenges lies in the very foundation, material procurement. From the elusive electrical steel to the financial conundrum posed by aluminum, our resolve was tested. The essence of any linear induction motor lies in the quality of its electrical steel. However, acquiring this crucial material in smaller quantities suitable for our project proved challenging. While the scarcity led us to explore alternatives, such as amorphous metal, the cost implications steered us back towards utilizing electrical steel for its optimal balance of suitability and affordability. Building the LIM track introduced another financial conundrum. The sheer amount of aluminum required posed a significant cost burden. Our engineering team embarked on a journey to optimize the track design, seeking a harmonious balance between cost and efficiency. The core of the LIM is its beating heart, and its preparation demands precision and foresight. From choosing cutting methods to determining assembly techniques, this phase presented its own set of intricacies. Laser jet and water jet cutting methods were the contenders in our quest for precision. While water jet proved effective, it introduced surface abrasions, impacting the performance of the LIM. The dilemma between precision and surface integrity forced us to reevaluate our cutting approach. The assembly of the LIM core unfolded as a meticulous process, presenting a choice between epoxy binding and a nuanced approach involving insulation spray and subsequent bolting. Our initial exploration of epoxy binding proved suboptimal, steering us toward a more intricate method, applying insulation spray on each sheet, followed by precision bolting. This nuanced assembly technique was adopted to achieve enhanced core rigidity, ensuring optimal performance. The assembly of the LIM core is where theory converges with practicality. Achieving the recommended gap between the LIM core and the track became a balancing act, and crafting custom mounts emerged as a crucial aspect. Ensuring the optimal 3 mm distance between the LIM core and the track proved intricate, striking a delicate balance to ensure optimal functionality without compromising safety became a cornerstone of our assembly process. Crafting custom mounts for the LIM core became a pivotal part of our assembly strategy. These mounts played a crucial role in securing the LIM core, ensuring stability and longevity. The operational phase of the LIM journey introduces a new set of challenges. Overheating, often a nemesis in electrical systems, demanded innovative cooling solutions and ventilation strategies. The design team navigated through various cooling options, eventually settling on a ventilation system within the aeroshell. Coupled with strategically placed fans, this solution aimed to dissipate heat efficiently, ensuring the longevity of the LIM. In the crucible of challenges emerged not only setbacks, but opportunities for innovation. The team's adaptability and inventive spirit came to the fore in addressing these challenges head-on. Our journey through the intricate world of linear induction motors and the Hyperloop pod has been a collective effort fueled by dedication, innovation, and unwavering perseverance.
I hope you all found the lecture informative and interesting. Thank you.